Well, hello. Good morning, everybody, or good afternoon, or good evening, whatever it may be, wherever you are in the world. Apologies for the wee delay there. I'll just introduce myself to get started. So I'm Professor Brian Nolan, and I'm the chair of the Masters in Astrophysics and Relativity here in Dublin City University. So what I'm going to do is take you through a few details of the program, covering entry requirements, covering the course content, talking about what you'll be studying in the program, talking about career prospects, and in particular, I suppose, the pathways from this program into research in the areas of astrophysics and relativity. So there's our schedule for the presentation. As I say, an overview, program structure and content, program requirements, career opportunities, and research opportunities. Okay, well, this program is now in its fourth year. It was introduced by the university, I suppose, essentially because there's a group of researchers in the university who have come together to form the Centre for Astrophysics and Relativity. So the program and the centre kind of emerged at the same time, I suppose, in response to the fact that we have a critical mass of people working in the university in this area, reflecting the fact that this is really a very exciting time in astrophysics and relativity. So, for example, just in the last few years, there's been 2 Nobel Prizes in physics awarded in this area. First in 2017 for the detection of gravitational waves by the LIGO research team, and then just 4 years ago for various black hole discoveries. For example, the image of the black hole at the center of the M87 galaxy, and theoretical work on black holes dating back to the 1960s. There are new telescopes, new international collaborations building large-scale telescopes that are coming on stream at the moment. And researchers in DCU Centres for Astrophysics and Relativity are involved across these kind of different efforts with research collaborators across the world. So it's an exciting time in this area of science. Well, the science has always been exciting, but it's particularly so at the moment. And I suppose there is a need then to develop knowledge in this area and to bring new researchers forward into this area. So I suppose very briefly, this is what the program is about. It's about the exciting science, but it's also about equipping students with excellent transferable employability skills. And we'll see that emerging over the next few minutes as I describe the program. So the program is a 1-year full-time or 2-year part-time MSc program. It has 90 ECTS credits. We have 2 semesters of teaching from the first semester from September to December, involving 30 credits. So in this first semester, you'll be attending classes, completing assignments, and doing exams. Same again in semester 2, which runs from January to April, 30 credits. We have about 4 or 5 modules in second semester. So you'll be attending classes, going to labs, completing assignments, completing exams. And then third semester doesn't really make sense, but the third part of the calendar year is spent during the summer working on an individual project. This is a very significant project. It goes for 30 credits of the degree award. So you'll start that project in May. Like I say, it's an individual project, so that means the projects are done by individual students rather than in groups and with individual supervision. So each student is assigned one researcher as their supervisor for this project. Okay, so the 3 legs of the degree are, well, it's called Astrophysics and Relativity. So you can probably guess what 2 out of the 3 legs are. They are, of course, General Relativity and Astrophysics. But the third leg, the other modules in the program, allow you to develop skills in computational science and in data analysis. And these 3, as the diagram attempts to indicate, feed off one another. So let me describe those three legs. First, there's the general relativity leg of the program. What this comprises is a module in semester 1 on differential geometry and general relativity. So differential geometry is the mathematics that's required for the understanding of and the study of and application of general relativity. So this is Einstein's geometric theory of gravitation that underpins our modern understanding of the gravitational field and all of the applications and settings in astrophysics and cosmology that require that precise description of the gravitational field. In semester 2, you look at some of the most exciting applications of this theory to the areas of black holes and gravitational waves, studying various different aspects of these things in black holes, looking at the theoretical foundations, looking at astrophysical black holes and the mechanisms that go into the formation and evolution of those, and then looking at quantum aspects of black holes, including famous Hawking radiation. In the module on gravitational waves, well, what's required there is a thorough understanding of the sources of gravitational waves. How do we describe these really highly energetic astrophysical events that, for example, the collision of black holes, of a pair of black holes, as the diagram is trying to capture there. How do we describe those sources of gravitational waves? How do we describe the propagation of those gravitational waves across the universe? And how do we detect gravitational waves? So that module covers all those areas. The second leg of the program is the astrophysics. In the first semester, there's a kind of an advanced foundational module. That sounds like an oxymoron, but essentially, I suppose what we're trying to get at there is the idea is that it's a broad module that provides an advanced introduction to the area of astrophysics, in particular the area of theoretical astrophysics. So what you'd be looking at there is how do we model using mathematics and computational approaches and fundamental physical principles, how do we model key astrophysical events, for example, formation of stars, formation of galaxies, formation of planetary systems, with an emphasis, I suppose, in particular on the roles played by plasmas and by magnetic fields. In semester 2, you specialize a bit more and look at extragalactic astrophysics on the one hand and high energy astrophysics. In extragalactic astrophysics, some of the material there covers such topics as the galactic formation, collisions of galaxies, the intergalactic medium, and exoplanets. In high energy astrophysics, you study some of the most energetic events in the universe, such as binary pulsars and gamma ray bursts, with some focus on the idea of how we observe these highly energetic events and how we model them. The third leg of the program, as I've mentioned, refers to we've titled it Computation and Data Analysis. So I suppose computational physics, computational science, and data analysis. So there's 3 modules involved there. There's a module on partial differential equations in semester 1, a module on data science and machine learning in semester 1 as well, and then a module on computational physics in semester 2. So partial differential equations you may recognize as a mathematics module. So differential equations are the kind of equations that we typically use in applications to model systems which have moving parts, essentially. It's well, perhaps not well known, but it is a fact of the matter that the ever quotable Einstein maintained that Isaac Newton's greatest discovery is that we can use differential equations to model the universe. So out of all Newton's incredible discoveries, this is the one that Einstein picked out as being the preeminent one, that we can use a particular class of mathematical equation to predict the evolution of the world around us. So given that we're looking at evolutions of systems involving galaxies, black holes, gravitational waves, stars, this clearly is a very important module. The data science and machine learning, I should say as well that these differential equations, they model all kinds of evolving systems. So it may be the focus in our program is on, of course, the astrophysics and the relativity, but these type of equations are also used in applications such as to, let's say the propagation of a pandemic around the globe, to weather systems, to finance systems. Anything with moving parts can usually be modeled using differential equations. In data science and machine learning, you'll be learning about those really important cutting edge technologies, information technologies that have vast range of applications. So again, in your assignments, you'll be looking at applications of the theory to astrophysics and relativity, but you'll be also picking up some really useful transferable skills that are used in almost all areas of enterprise, business, and research these days. Computational physics is about advancing some programming skills to develop the specific skills that are required to write and apply and use computer programs in the setting of the study of physics. Okay, so program requirements, and I see that there's a question in the chat there about what areas of mathematics you should have studied as an undergraduate, particularly for general relativity. Thanks, Verena, for that question. Okay, so I think I can cover that with this slide. So the program requirements, and at the end I'll give you a link to the course webpage so you can look at this in a little bit more detail. So the basic requirement is a recognised primary degree equivalent to the Irish National Framework of Qualifications Level 8, and you'll be able to see how that translates into corresponding qualification frameworks in your own country. So a primary degree in physics or astrophysics or theoretical physics or mathematical sciences or applied mathematics or a closely related field, for example, engineering. So, for example, some flavors of engineering would indeed equip you with sufficient mathematics and physics to cover the prerequisite knowledge for the program. We look for a minimum of a second-class honours grade 1 award for the program. So the question there about which areas of pure maths should you have studied. So basically, if you do have a physics degree, you've probably done the mathematics that we would require. So it usually amounts to having studied mathematics for about 2 years, maybe 2.5 years. So you would certainly need to have studied calculus of a single variable, so differential calculus, integral calculus, calculus of several variables. So again, knowing how to evaluate derivatives and apply derivatives and evaluate integrals in the context of multivariate calculus, linear algebra, and some ordinary differential equations. So these are, I suppose, these are the foundational parts of mathematics that essentially all physicists or engineers or astrophysicists would have studied at undergraduate level. There's a corresponding set of topics in the physics prerequisites, and again that corresponds to the foundational material that all physicists or theoretical physicists or even mathematical scientists or applied mathematicians would have studied over probably the first couple of years of their undergraduate program. So like I say, there's a link to the course webpage at the end of the presentation. So if you go there, you'll find a little bit more detail about that. But just on that specific question, which areas of mathematics? Okay, I see I've answered your question, Verena. And which programming language do you use? Okay, so the program is essentially agnostic with respect to which programming languages. So in the computational physics, the lecture there has structured the course so that you can use Python or Java or C. In the data analysis and machine learning, there is, of course, an emphasis on Python and R. These being the most important programming languages in the areas of data analysis and machine learning. So careers, well, I suppose the first port of call here is just to point out that this is an excellent way to begin a career in research. So you get the preparation both in terms of knowledge and skills, but also with a master's degree. What we found is that having a master's degree in the relevant area greatly increases your prospects for a PhD research scholarship, both within Ireland and abroad. So a lot of our graduates have gone on to PhD studies, some of them here in DCU and others in other countries and all around the world, really. Well, we have students who have gone on to PhD study in India, in the UK, in Germany, in Portugal, and we have people who are currently submitting applications for PhD study in the US. Okay, so that's I'm going to sort of divide this career slide in two, as you see. One is what I've just said about the master's program providing an excellent pathway into research, and the other is everything else. Okay, so as I've mentioned, the program gives you the opportunity to study this exciting cutting-edge science, but at the same time equips you with terrific transferable skills, in particular in computing and data analysis. So we have lots of our graduates. It's probably more of our graduates going into other careers, and they've gone into areas like information and communications technology, into data analytics, into engineering, into banking, finance, and business consultancy. So a program like this is equipping you with, well, the technical skills in terms of the data analysis and the computational science, but also the more generic transferable skills in terms of analytic abilities and problem-solving capacities and communication skills as well through preparing and presenting your project. Okay, so that brings me nicely into saying a few words about the project. As I've mentioned already, when discussing the calendar for the program, all students undertake a project over the course of the summer. In doing this work, you have individual supervision by CFAR researchers, Centre for Astrophysics and Relativity, that is, of course. So each student is assigned to an individual supervisor. The supervisors, at the beginning of the second semester, what we do is we propose a list of project titles, and we provide all the students with a brief description of the various projects, and then students submit their preferences for those projects, and we do our best to ensure that everybody gets their highest preference of the projects. Some project titles some areas are more popular than others from one year to another. And so we do have to apply a bit of selection on the basis of results from the first semester. But essentially every year so far, we've had students, all of our students have, the vast majority of our students have had their first or second choice project. And we've had, I think, maybe 2 students over the first 3 years who were offered their third choice of project. So with that, you have the immediate possibility not just of working in your project, but of working with the supervisor on a PhD funding application. Just to give a sense of the kind of project areas that people have taken on over the last couple of years, under the general relativity heading, we've had people working on projects on black hole physics, on gravitational waves, on the problem of motion in general relativity, which is immensely complicated and very important for deriving the form of gravitational waves that we expect to detect over the next couple of decades. We've also had students who are studying the quantum aspects of black holes, so looking at quantum fields in curved space-time and veering into the area of quantum gravity. And then there's my own area. I'm more of a mathematical physicist, a mathematician than a physicist. And so I've supervised projects in mathematical relativity. So looking at mathematical problems that arise in the context of general relativity. On the astrophysics side, students have undertaken projects studying astrophysical plasmas, studying black hole formation, studying planetary disk formation, studying solar weather even, and looking at observations of exoplanets and trying to interpret the data and look at the population statistics and formation channels for exoplanets. Students have also taken on projects on high energy astrophysics and studying gamma ray and X-ray sources, and also looking at the science of this new generation of some of the new generation of telescopes that are going to be coming on stream over the next few years. Okay, so that brings me to the end of the presentation. I'm very happy to take questions. If anybody else has any further questions to throw up in the chat there, we can have a look at those. Those are my contact details. So I suppose the 2 key things there are just my email address. Very, very happy to answer any queries about the program, and further information you'll get from the short link there, dcu.ie/dc742. So that'll give you full details of the program. I've been very brief here, of course, but you'll find more details about the modules that you'll be studying in the program, about the prerequisites as well. There's some description under the heading of each module for what kind of things you would need to know coming in, and also a little bit more about the research prospects. And you'll find a link there to the CFAR website, so you can find out a bit more about the research group that we have here and the kind of research that people are doing. Okay, I think